Okay, so for my data structure that I will be discussing is called a Bloom filter, and this was created in 1970 by Burton Howard Bloom. And this is a probabilistic data structure, which means that it uses probability to determine whether an event is either true or false. So in this case, we have a Bloom filter, which determines whether a element is a member of a given set or it's not, whether it's present or not present in the set using probability. So in this case, here's an example here. We have element X, and what a Bloom filter does very generally speaking is that it tests whether X is an element of set P. So with this, the output then would be false. And when determining this output, it has a 100% accuracy of it actually being false. So therefore, there's in no way that X can be present in P when it is false. However, in this example here, we have S containing the word cow, so element X. So therefore, this would then be true. And when determinate when its output is true, it has roughly a 90% chance. I'm sorry, not chance, but accuracy of this case being true, which then means that it has a 10% chance, roughly, to be considered a false positive. And what that means is that even though it's not in the set, it detects it uh, using hash functions and likewise, which I'll get into in just a second, that it is in the set. So how a Bloom filter works is that before an element gets inserted into the structure, it gets hashed into hash using hash functions and hash indexes, which I will describe in just a moment. So those the amount of hash functions is very I'm sorry, this this number here, 90% and 10%, it's determined using a certain formula that is based off the amount of hashes and hash functions, I should say, used when generating the hash indexes. So it's let's get into how it's implemented here. So a base data structure of um the Bloom filter is known as a bit vector. So I just drew up a bit vector here with 10 elements, and I just indexed it 0 through 9. And I initialized, as you should, the uh, bit vector to all zeros, meaning that there's nothing in each cell. So, like I mentioned before, it uses hash functions. So in this case, I have two hash functions. I have f of x and g of x. And right now, for this example I'm going to give you, I'm going to insert these three elements, pig, dog, and cat, into this data structure here. So this bit vector, I should say. So f of x, when pig is first hashed through f of x, it has a hash index of 5. So therefore, 5 it points to 5, and then g of x is 9, so 9. So when it points to it, it then makes this 1, makes the value 1 to that index, meaning that it already points to it. So uh, when we want to insert dog, it's 4 and 5. So 4 and 5. Something I should also mention is that uh, when inserting elements into a Bloom filter, there's only going to be one unique element. So two or more unique elements can share the same hash indexes, but it cannot share all hash indexes. So in this case, dog is 4 and 5. 5 is already pointed to, so it can't be changed to a value more than 1 because it's a bit vector. But it's alright because uh, it has two different values. When using hash functions, you should typically use more than two functions, but for this example, I'm just being very simple here and only providing two. But with by including more hash functions, this 90% chance, I'm sorry, 90% accuracy and 10% chance of having a false positive occur, uh, this false positive would decrease, and this instance of the output being true would increase when you use more hash functions. So it's important to use several hash functions depending on the amount of elements used when inserting the into a bit vector. So uh, now I'm going to ask the question: how can cow be inserted into this bit vector? So it points to 1 and it points to 5. It says, hey, there's a value in 1, there's a value in 5. Therefore, cow already exists in this data structure. So that's what a false positive means when its hash indexes are already both or all of them are included in the bit vector. So that's why it's strongly recommended to not create this overflow of um, indexes. So if I want to insert it, it would then have to, one of these numbers have to be changed to a number that's not utilized, or both of them even. Or by using more hash functions. So why are Bloom filters important? Well, they're used everywhere within databases and many applications. Along with the variations that are on the screen right now, Bloom filters, there are some that can output a message that says, for example, username already exists, or something like that along those lines, to detect whether a username is unique or not within a given set. So that could be very beneficial to applications and likewise. And with the many variations along comes its benefits. So one being standard, the second being compressed, three being counting, and four invertible. So they're basically all very similar to each other. Um, they're just slightly varied in the sense that um, it would be more efficient to use this than that, depending on how you use a Bloom filter. So, for its time complexity of a Bloom filter, it can never delete an element of within the Bloom filter that's used as another data structure or implemented. That can even be implemented with the counting Bloom filter, but its complexity in this sense, for all, very generally speaking, for all Bloom filters, it can only search and insert, and that is has a complexity of complexity of OK, where K is the number of hash functions, I should say, that you use to hash a an element, and this is one of the only few data structures whose time complexity does not depend on the number of elements, because the elements never really enter the data structure, only their hashes. One more thing I'd like to mention is that for its implementations, being C++, Python 3, and Java, it's implemented very easy. This data structure, it uses libraries to use specific operations and likewise to insert a Bloom filter. So thank you for listening.